Alpha particle monitoring. First of all, where and why is the monitoring of nuclear power plants done? The Nuclear Regulatory Commission maintains very strict requirements for radiation emissions and stray radioactive materials from nuclear power plants. Power plants must be built to specifications that keep radioactive material releases as low as reasonably achievable, or what is also known as ALARA. The Nuclear Regulatory Commission maintains very strict requirements for radiation emissions and stray radioactive materials from nuclear power plants. Power plants must be built to specifications that keeps radioactive material releases as low as reasonably achievable, or what is known as ALARA. Additionally, reactor operators must monitor any and all release of radioactive materials and radiation in the air, surface water, groundwater, drinking water, shoreline sediment, and such animal materials as milk or fish tissue. At least 2 nuclear particulate monitors or air stations must be installed at nuclear plant perimeters for them to remain compliant. Additional government monitoring initiatives include RADNet and the National Council on Radiation Protections and Measurements. RADNet is the EPA-directed national radiation monitoring system. It was established to track national and regional ambient radiation levels in air, precipitation, and drinking water in order to evaluate their overall impact on the general population and on public health. RADNet also acts to quickly quantify and assess contamination in the case of a radiation incident or emergency. The National Council on Radiation Protection and Measurements was chartered by the U.S. Congress in 1964. It is also tasked with developing methods to rapidly assess and treat widespread nuclear exposure in the event of a nuclear accident. In all of these situations, what types of radiation are being monitored? Nuclear facilities are responsible for monitoring each type of emission according to the specific hazards presented to employees and to the environment. These emissions can include alpha particles, which are helium nucleuses emitted by some radioactive materials, beta particles, which are electrons or positrons emitted during radioactive decay, and/or gamma rays, which is energy released by the radioactive decay of atomic nuclei. Beta and gamma radiation monitoring is accomplished by measuring either the particle excitation and/or ionizing effects in gas ionization chambers, Geiger-Müller counters, scintillating materials, and semiconductor detectors. These measurements can be conducted in real time or as a function of dose rates. Alpha particle monitoring can also be conducted by evaluating particle excitation and ionizing effects, but unlike beta particles, alpha particles are sufficiently large to be collected on the surface of membrane filters. This presentation will be focusing on the filter membrane collection techniques of alpha particle monitoring. One of the challenges in radiation monitoring is to detect the non-natural radiation signal above the naturally occurring background radiation levels. One way to begin this differentiation is through the implementation of CPAMs. CPAMs and alpha cams can be installed in the perimeter of nuclear power plants to monitor nuclear emissions. CPAMs, or continuous particle air monitors, and alpha cams, or alpha continuous air monitors, are used to assess airborne particulate radioactivity. They utilize a pump to continuously pull air through a filter, collecting particles that contain radioactive material. Gas monitors are systems that instead employ a radiation detector to evaluate air in real time. CPAMs and alpha cams can operate with either a fixed or a moving filter. In both, the sampling pump pulls air at a constant rate through the monitor and the filter rather than pushing it through. Millipore Sigma Fluoropore PTFE membrane filters are highly suitable for both CPAMs and alpha cams. Unlike fibrous filter media that traps particles in their matrix, Fluoropore PTFE membranes collect particles on their surface. Surface collection provides better detection efficiencies and improved resolutions for alpha spectroscopy and better data collection. Fluoropore membranes are available in 3 and 5 micron pore sizes. Each have their own advantages. The smaller 3 micron pore size provides a higher resolution. The larger 5 micron pore size has a very low pressure drop and greater throughput capacity, which minimizes the number of filter changeouts. The PTFE surface collection of fluoropore membranes keeps particles closer to the detector, which provides better detection efficiencies and lower FWHM measurements. As you can see on the left, the 5-micron filters have very high flow rates, up to 12 liters per minute per centimeter squared, while, as you can see in the center graph, the 3-micron filters have a very sharp alpha peak resolution of 350 kiloelectric volts FWHM. In the spectrum on the right, fluoropore filters are compared to competitive cellulose filters and used for this application. Both 3-micron and 5-micron fluoropore filters are well suited for alpha cam use. In conclusion, under the NRC, power plants have an obligation to keep their radiation emissions as low as reasonably achievable, or ALARA. Each nuclear facility is responsible for monitoring each type of emission according to the specific hazards presented to employees and the environment. Fluoropore membrane filters offer high flow rates and sharp alpha peak resolution for alpha particle monitoring.